In this video, I will explain you the working of AC generator. Now, we know the purpose of using AC generator is to produce alternating current. What is alternating current? Alternating current is nothing but current that continuously changes its magnitude and periodically change its direction. Say in this way. Yeah, now this is the intensity of current. This is time on the x-axis and intensity on of the current on the y-axis. Now see, this is the whole thing is the one time period. Okay, in one time period we can see two parts. One is till here, one is till half time period, and rest of the part is from half time period till it complete one revolution. Now see, value of current at any moment is different from the previous, and it is continuously increasing to a maximum point, then that start decreasing from that point and it comes to zero finally once it reaches half of the time period. You know what is half of the time period, right? This thing is for the one complete wave, it is full time period. Now this is the half time period. Now what is happening there? Let's say we have a circuit. Okay, in this circuit, current start increasing, see, from zero, and that increases, go all the way till maximum value, and from that value the value of current decreases. But is there any change in direction? No. So current starts from zero, so there is no current here. From here current starts from zero, increases, so 0, 1, 2, 3, 4, 5. So in the same direction, so current is going in the same direction and the value increases initially, then that gradually decreases to 0. See, 5, 4, 3, 2, 1. So assume that current is going from top till the tip. So initially 1 ampere, 2 ampere, 3 ampere, 4 ampere, 5 ampere. Now in the same direction, 4, 3, 2, 1, 0. Now the current in this circuit is 0. Now current reverses the direction. Now initially current was going in this direction. Now current is going in this direction. So from here starts from 0. Now 1, 2, 3, 4, 5. Now see, current reverses the direction in opposite direction. From there it reaches the maximum value in the reverse direction, then that starts decreasing to 0. So once again I'll repeat, from current at this tip it will start flowing in this direction, 0, 1. So this is the direction, 0, 1, 2, 3, 4, 5, then 4, 3, 2, 1. Okay, now current in this direction becomes 0, and in this direction it starts increasing, 1, 2, 3, 4, 5, maximum value in the reverse direction, and 4, 3, 2, 1, 0. Now that is AC current. So periodically that changes its direction, and at any moment continuously that changes its magnitude. Continuously magnitude is changed, and periodically means, see, after half time period then the current flows in reverse direction. After next half, in the next half it is in the opposite direction, in the next half it is again in the opposite direction. Now this is AC. So one direction opposite, next half time period opposite positive direction, next half negative direction, next half positive. So in this way current will go through the circuit. This is AC current. Now how to produce current in this way, that we will learn in this lecture. So this will be done with the help of AC generator. Now I will introduce you different part of which the AC generator is made up of. So first thing is rotor coil. This one is the rotor coil. So it is made up of best quality copper. So why I am mentioning best quality copper? This is made up of a material that has got approximately no resistance. Okay, so it is made up of very good conductor. So I could say that it is made up of copper. Copper is a very good conductor. Now see, this is a coil, and of its one end is attached to a commutator ring. Okay, this is called as commutator ring. I will explain you the purpose of commutator ring after stator coil. So this one is just a copper coil. Now next one is stator coil. Stator coil, now I have mentioned you a permanent magnet in this video. Instead of this, it will be temporary magnet. Temporary magnet means whenever current passing through it, that will act as magnet. These are called as electromagnet. Only with the help of current it can behave as a magnet. So anyway, the help of stator coil is nothing but producing magnetic field around the rotor. So this is the rotor, this one is the rotor. Now this rotor will be capable of rotating around one axis. Now around this axis, this will be able to rotate. Now who will be rotating it? Now that it is fitted with turbine blade. Okay, turbine. Now whenever water is pumped on this turbine blade, the water will get, this blade will get the energy. That is nothing but energy stored in the dam. So now we have dam at a very high elevation. From there, water will come through a pipe, and this is penstock. Now from here, water, see here the whole energy of the water is potential energy. Now while it is coming through the penstock, it will be converted into kinetic energy, and here it will be maximum kinetic energy. With that kinetic energy, through the nozzle, water will be coming out. Now I will keep a turbine blade here, a turbine. So what will happen when the water, get impact with this turbine blade, the turbine will get an energy, and with that energy, this turbine will be run. Okay, now turbine has got an energy, this turbine will be rotated. Now the turbine is connected to the rotor coil. Now rotor coil also will rotate. Simply, this needs certain amount of energy. It can be due to what? Steam. See, steam turbine we have, right? So there we are going to convert the energy contained in the heated steam, superheated steam. Here we are going to use the energy contained in water, which is stored at a height, any value h, especially in elevated height, dam or any kind of reservoir. Okay, so there is one kind of energy conservation here, energy conversion here. Water energy stored in the water in the form of potential energy is being converted as mechanical energy at this blade. Now with that mechanical energy, turbine will be operated. So this will get an energy, and with that energy, that will keep rotating. Now this is connected to a rotor blade. Now the rotor blade will start rotating. Now where is this rotor blade kept? See, we have a stator coil here. It's a magnet. Either you can consider it as a coil, or just consider it as a magnet having a north pole and south pole. So the magnetic field will be in this direction. Now see, now our coil is being rotated in a magnetic field in this way. Let's say this is the coil and this is the direction of magnetic field. Direction of magnetic field and magnitude is not changing, but our coil is being rotated. Now in the previous chapter we have learned that there will be an EMF induced in it. Why? Because our coil at any moment it is cutting the magnetic field line. Now whenever magnetic flux linked with the coil changes, there will be an EMF induced in it. What is this induced EMF? As per Faraday's law of electromagnetic induction, we have learned that the value of induced EMF in a coil which is rotating in a circular coil or any closed coil which is rotating in a magnetic field. What is that value? E is equal to E0 sin omega t. This is nothing but EMF induced in a coil which is rotating in a magnetic field. And the value of E0 also we know, NBA omega sin omega t. This was the equation we have derived, right? Where N is the number of turns in this coil and B is this magnetic field line and A is nothing but area of, so area vector, what will be the direction of area? If this is the area, this will be the direction of area vector. Okay, now this is the direction, now this is the direction. So now B is the intensity of magnetic field, N is the total number of coils, turns in this coil, A is the area, so that is nothing but length into breadth of this coil. Omega is measured in radians per second. So 10 degree per second, 30 degree per second, maybe here 90 degrees. So for the whole rotation in this way. So see, starting from this position, okay, this is the whole rotation. For the whole rotation, see, whole rotation. From here, this is the whole rotation. Okay. Now for the whole rotation, if it is taking 4 seconds, now I can say that 360 degrees covered in 4 seconds. Now in 1 second, it is 90 degree covered. 90 degrees nothing but pi by 2. So this is pi by 2 radians per second. So in this way we can find the value of omega, and omega basically, if you know the time period, omega is equal to 2 pi by t. In this way we can get the value. So in this example, we know the time period 4, right? So I can keep it as 4. So this will be pi by 2. The same value we have derived here. Now anyway, omega we will get, and what is this sin omega t represent? Sin omega t says that this induced EMF in the circular coil will not be constant always. Now see, we have a coil, okay, and let's say this is the direction of magnetic field, okay, this is the head and this is the tail. Now tell me, what is the direction of angle, what is the angle between magnetic field line and area in this case? See, always I have told you the direction of area vector will be perpendicular to the area. Now this is the area, perpendicular to the area will be the direction of area vector. Now this is the magnetic field. Now when magnetic field lines are going in this way, the angle is 0. Now keep in this equation, if I am keeping the angle as 0, so sin omega t can be written as NBA. So omega t is nothing but theta. So omega t is nothing but theta. So instead of omega t, we can directly substitute the theta. Okay. Now here in this case, see, here in this case the angle is 0 because magnetic field and area vector are in the same direction. Angle is 0. Now this is rotating. Now here what is the angle? Angle is, this is my magnetic field. Direction of magnetic field will never change. So this is the direction of magnetic field and this is area vector. The angle is 90. Here 180. Now next will be this 90. 0. Now once again, see, this is the initial position that rotates. Now the angle is 90. Now the angle is 180. I can't rotate in this way, so I am keeping in this way. Now the angle is 270, 360. Okay. So different cases. First case in the red color. Now this I am going to mark in red color, the top view. Now the black color will be nothing but direction of magnetic field. Now this is the direction of magnetic field. Okay, now see one more thing. Area will be, if let's say if this is the area, then area vector will be in this direction. Okay, so in the first case, this is the area, right? So I am going to keep area in this way. Now my direction of area will be in this way. Okay, so that is in red color I am going to mark direction of area, not the top part of this current carrying conductor. Okay, so that will be perpendicular. The red color, the direction of area will be perpendicular to this. So this is the initial direction. Okay, now, okay, see. Now magnetic field is in this way. Okay, this is the actual direction of magnetic field, and what I am going to do, I am going to now water hit on the turbine blade get energy, and that is being rotated in this direction. Now this part, this is a circular loop, right? So this is a rectangular loop. Okay, now when the rectangular loop is being rotated in this direction, now this arm or this part of the conductor is moving inward direction. See, now it is being rotated in this way. Now this conductor, this portion is moving inward and this portion is moving outward. See, rotating, and this portion is moving inward and this portion is coming outward. Now, what will be the direction of current while rotating in this way? Now, we will use Fleming's left hand rule. This is magnetic field, right? Now, it is being rotated in this direction. See? This is moving inward. This side is moving inward. So, this is the direction of movement. Okay? Moving inward, magnetic field and current will be in downward direction. Now, will that be a constant value? No. How we will get the value of current? We know that EMF, this EMF will be creating a current, and we know V is equal to IR, or I is equal to V by R. Now, this EMF will be induced across this resistance. So, the whole thing will induce an EMF and there will be an EMF available across these 2 points, and that is connected across this resistance. Correct? Now, what will be the value of current here? We know that this is EMF. E0 sin omega t is the EMF. So, induced current is equal to E0 sin omega t divided by resistance. So, E0 by resistance into sin omega t, or this value will be E0 by resistance. I can name it as I0 sin omega t. Why I have done this? Just to give you the idea that this current won't be constant. Now we got to know that the current will be moving in this direction, but that will never be constant. Why? Why it is not constant? Because we have a function called sin omega t here. So depending on the angle theta, the value of current will also change. Now, see here, what is the angle? This is the direction of area. Angle is 0. Okay, so that is the first case. I'll mention it here. This is my magnetic field, and I am creating my I am keeping my coil in this way. Okay, this is the direction of area. So my area, both of them are in the same direction. Okay, so angle theta is equal to 0, and that is at time is equal to 0. Okay, now we will substitute, instead of omega t, I can substitute 0 and the value of current will be 0. So I will make a table here. So different value of current we are going to check for the different value of angle. So theta I am going to check for 0, 90, 180, 270 and 360. And I will also check value of EMF. This is very important table, okay? Now, see, so at angle 0, the value is, I will substitute 0 here and I will substitute 0 here. So sin 0 is 0, sin 0 is 0, 0 multiplied by I0 will be 0, 0 multiplied by I0 will be again 0. So the value of current, both are 0. Now at angle 90, and what will be the case? See, this rotated and became in this way. Now this is my area vector and this is magnetic field. Magnetic field in this way, area vector in this way. So I0 sin 90, sin 90 is 1, and here also E0 sin 90, sin 90 is 1. So here this will become I0 into 1 and E0 into 1. So that will be I0 and E0. That is the maximum value. Okay, the maximum value of sine function is always 1. So the maximum value of this function will be nothing but I0 cannot change, and that is the maximum value of sin omega t, that is 1. So the maximum value of current in this function will be always I0, because sine become maximum when the value becomes 1. Okay, now at 180 means, at 180 the value means, see, from here it has rotated in this way, that is 90. Now 180, area is in this direction. See, area is in this direction and magnetic field is in this direction, angle made is 180, opposite to each other. Okay, sine 180 and sine 180, it is 0. Sine 0, sine n pi is 0. Okay, so sine 180 is nothing but sine 1 pi. Okay, so this is 0 and this value will also be 0. So these are 0 and 0. I0 sine 180 is 0, E0 sine 180, that is also 0. Now at 270, so this is the first case, rotated in this way. Now 270. Now see, from here while it goes to 270, see the difference? It goes in this way, right? Now 360, it goes in this way. Now see, this is the current position. So 0, this is the initial position. Now it become 90, now this become 180. Now while it comes, now this was our side, right? Now from here while it comes in this direction, now this conductor will be, at that position. See, once again I'll repeat, this is our initial side. Now this side has gone here while it become 180, 90. Now it has gone here while it become 180. Now this side is coming towards me. Okay, in the next rotation it is coming towards me. Now while it is coming towards me, we will see the direction of current. Okay, so this is the direction of current and this is the direction of magnetic field and this will be the direction of current. See, that is very important. In the same conductor, in the same arm, I am going to call it as arm. In the same arm, the direction of current is different at two different positions. When it was here, when it is coming inward, the direction of current is downward. Now the same conductor, when it is coming towards me, direction of current, magnetic field, the direction of current is upward. See, the direction has got reversed now. So the value is 270. So sine 270 is minus 1. Here also it is minus 1. So minus 1 into I0 will be minus I0. And here also that will be minus E0. Direction of current and direction of potential has changed. Potential difference has changed. 360, we know that sine n pi is 0. So 360 is nothing but 2 pi. So sine 2 pi, here and here also it will be 0. This is very, very important. So output from AC generator will be in this way. With respect to different angle, the value of direction of current and magnitude of current will be completely different. But we have seen that the whole process will be repeated in the next revolution. Would be the same in the next revolution. Would be the same in the next revolution. So I can say that this is a periodic motion. Okay. Now, and what is the function of commutator ring now? See, this will now be connected to a ring. Now whenever the whole thing is rotated, this ring also will rotate. This ring also will rotate. Now how can we take a current from this ring? By connecting the carbon brush here, and along with the carbon brush we will keep a spring here. So this will actually be in this way. Just imagine the way that rotates. Okay, so the whole coil will be rotating here, and the whole coil connected with this arm also will be rotated, would be rotated. So this will keeps on rotating. So I can't solder or I can't attach any wire to this. If I am attaching, what will happen? That will rotate along with the coil, and see, finally at one position that the whole rotation will be stopped due to the tension. So what we will do, this is a detachable spring, a carbon brush. So we will keep a spring here, and with that spring we will connect one carbon brush, and we will keep it pressed with the ring. So whenever the ring is being rotated, there will always be a contact of the carbon brush with the ring, and that will always be in a pressed condition because there is a spring attached to it. So always we can take current from here, though there is no permanent contact, there is no permanent attachment. So this would be in this way. So this is the carbon brush. See, this is the carbon brush. So there is no permanent. If there is a permanent attachment, then that whenever the coil is rotating, then that will also rotate along with it. But instead of that, I am just keeping a contact. Now this, when this rotates, see, there is a contact, but actually it is not permanently fixed. See, that this brush will be keeping a contact with the ring, and that will be rotating. Okay, now we have got the table of different value of current and EMF with different angle. Now we will see the curve, the graph that represent the variation of EMF and current in an AC circuit. So this is XY axis. When time t starts from angle 0, the value of current, so I will first represent the value for EMF, because EMF, when it is connected across an external resistance, that became a current, right? So EMF is the source here, that is the cause here. Okay, so the value of EMF, initially it is 0, and at 90 the value has become plus E0, that is maximum value of E0. Now at 180 the value has came to 0. Now at 270 the direction of EMF is reversed, and that is maximum in the reverse direction. Now at 360 the value is 0. Okay, started from 0, E0, so gradually increases in one direction, increases and become maximum. Then from 90 to 180 it becomes 0 from maximum value. Now from 180 to 270, from 0 that increase the value to the maximum value, but in reverse direction. Now at 360 the value is 0. Okay, now how to get the value of current? Value of current is nothing but, see, this is the value of current. Value of current is voltage E0 sin omega t, V divided by R we know. So value of R will always be greater than 1. So when we are dividing a value with a value greater than 1, then the total value will be decreased. So basically we are dividing I, just consider that the value of resistance is 2. Now it will be just a half value. Okay, see, let's say E0 value is 5 and this is 5 sin omega t. Now if resistance is 2.5, then I is equal to 5 divided by 2.5 sin omega t. That will be 2 sin omega t. So my point here is, when we are dividing with R, then the value of then the total value decreases. So the maximum value of I, which is I0, that will always be less than value of E0, because we are dividing E0 with the resistance R to get I0. Okay, now this is very important. I0 is equal to E0 divided by R. This is a pure resistive circuit. I will tell you what is the meaning of pure resistive circuit in the coming lectures. Now when we are only connecting resistance in that circuit, then that is called as pure resistive circuit. We have capacitors and inductors coming up. Okay, now so here I0 will be a value less than E0, so that will also be in phase. I will also tell the meaning of in phase, but anyway, according to the value of E0, the value of I0 also increases and decreases. Now it is 0 to E0, E0 is the maximum value, so here also 0 to I0, I0 is the maximum value and the value of I0 is E0 divided by R. Now it has came to 0, now it is going and the current will be in opposite direction. Now from minus I0 it increases the value to 0. Now this is E0, maximum value of EMF, and this is I0, and the value of maximum value of current is E0 by R. Now from now onwards I am going to represent AC in this way. So my thumb I am going to represent as my x-axis. Okay, now see this finger, pointing finger, index finger, I am going to represent for the magnitude of current and voltage. See, now as I am going, my index finger increases, then it decreases, and now I have to do it in this direction, increases and decreases. See, now increases, decreases in the opposite direction, increases and decreases. See, x-axis, now current and voltage increases together to maximum value, then decreases, now in the opposite direction, increases, then decreases. See, increases, decreases, increases in opposite direction, then decreases. Okay, so I will conclude everything in 1 minute. That initially we have our area in this way, okay, in this way, where the magnetic field was in this direction, and this is the area vector. Area vector is in this direction. Okay, so both of them are in the same direction. Now see, this is direction of magnetic field, this is direction of area vector. See, basically area is in this way. Okay, area is exactly in this way, but the direction of area vector is in this way. Okay, so both of them are in the same direction. Now when it rotates from here to this position, now this is the direction of magnetic field, and now area from this position, it is rotating in this way. So our area vector will be in this way. Now that makes 90 degree with magnetic field, and this is our area. Now this was the area before, this is my area, and this is the direction of area vector. Now in the next position, from this was the initial case, now this, then this. Okay, so our area vector will be, see, now from area in this direction, this is the top view. From this direction, area is rotated in this way. See the top view from the top. Now area will be from here, it will be rotated in this way, and this is area vector. So this is 90, and this will be 180, just the opposite. Okay, magnetic field and direction. In the next position, next I will mark here itself on the top. Direction of magnetic field won't change. Now this will be the direction of magnetic field, area vector. This will be the direction of area vector. This is area, and this is the plane, the top. In the next position, this is the direction of magnetic field, and this is again the direction of area vector. See, area is initially making 0 angle, then area makes 90 degree with the direction of magnetic field. Now area makes 180 degree with the direction of magnetic field. Now area makes 270 degree with the direction of magnetic field. After that, it is in the same direction, 360 degree. So in these positions, we have drawn the current I is equal to I0 sin omega t, and that will be starting from this position 0, 90. Okay, so this is 0, and this one is 90, this one is 180, and this one is 270, and this one is 360. So I can say that this is 0, t by 4, 1/4 of the total time period. 1, 2, 3, 4 portion is the whole time period. So this is t by 2, this is 3t by 4, and this is t again. Okay, so from 0 to t by 4. So this is 0, and this is at t by 4 or angle 90 or t by 4. This one is angle 180 or t by 2. This is angle 270 or 3t by 4. This is angle 360 or t. Direction of, this is the value of current. Maximum value of current will occur at 90 and 270. 90 and 270. Similarly, this is the voltage, and the value is V is equal to V0 sin omega t. And maximum value of V0 will occur at the same place where I0 occurs, and that is at either 90 degree. 90 degree can also be written as pi by 2. So I will mention it in pi by 2. 0, pi by 2, 0 radian, pi by 2 radian, then pi radian, then 3 pi by 2 radians, then it is 2 pi radian. Okay, so 0, this is 0, this one is pi by 2, this one is pi, and this is 3 pi by 2, this one is 2 pi. So any of the way, any of this method or any of this representation you can learn. So sometime it would be asked in radians, sometime it would be asked in degree, sometime it would be asked in time period. So this one is very, very, very important, the variation of voltage and the variation of current. So this graph can only be, the variation of current can only be represented in this way for a pure resistive circuit. When it is, values other than components other than resistance like inductor and capacitance, we can't draw the value of current in this way, the variation of current in this way. Okay.